Okay, let's get back to probability. This is Module 4, Part 3, How to Solve Probability Problems. Over the years of teaching statistics and probability, I've found that many students, when you talk to them about unions and intersections, they seem to understand what those events are. But when it gets time to actually solving word problems, they have a very difficult time. And I suspect that one of the reasons for that is they don't go about the problem correctly. So I'm going to suggest to you a way of attempting to solve some probability problems. We're going to start you off real easy. Read the problem. Except don't do what most students probably do initially. Most students just want to grab the numbers they're given and start to plug them in formulas. Before you do that, you have to be able to identify the variables and their outcomes in the problems. You have to know what the variables are, what the complements to different events are, and so forth. And it really helps to set up some notation for those variables. Now, all of our formulas used A's and B's, and A complement, B complement, but you can use any letters of the alphabet you want, and the formulas, of course, still hold true. But I think it's very important to do this first before you try to tackle the numbers. Once you've done that, then you can go back to the problem and try to write down what I call the given information, or all the known probabilities. And take care as to what kind of probability each is. Did the problem give you an intersection? Did it give you a union? And this is where those key words that we talked about earlier are important. If I tell you that 40% of the people are either male or have green eyes, or both, that's a union of two events, this or both. If I tell you that 40% of the people are both male and have green eyes, I just gave you an intersection, this and this both. So write down everything that you know. Also, take care to make sure that you include complements to any events. Then identify the probability of interest. In other words, the problem is going to ask you to solve for something, or maybe several things. Again, they might be asking you for a union, an intersection, a conditional, or some other type of probability that we haven't even gotten to yet. Now, at this point, one of two things usually happens. Hopefully, most of the time, you can solve for the probability of interest by simply using the formulas that we've developed here, what I call the plug and chug method. The problem might give you certain probabilities, then you can simply plug them in the formulas and get the probability that you're looking for. Sometimes that doesn't work, though. There may be times when you need to use a table approach or some other approach to help solve the problem. As I said earlier, there's lots of ways to tackle probability problems. Some people like to use tree diagrams, some people like to use Venn diagrams. I'm going to show you a little table approach that I use quite a bit to help solve some problems. Let's do a problem. Let's do sort of a typical word problem. In a particular class, 40% of the students are male, the rest female. 20% of the students have blonde hair and the rest do not. Out of the male students, 1/8 are blonde. And then I ask you a bunch of questions here. Again, before you start using the numbers and trying to put them in formulas, identify the variables here. One variable obviously is sex, with two outcomes, male and female. And the other variable here is hair color, again with two outcomes, the blondes and everyone else. This is an example of what I call the 2x2 case. I gave you two variables, and each variable had two outcomes. Sometimes we'll get to variables with more than two outcomes. We'll get to one of those later on, in fact. Okay, once we've identified the variables, we can start to set up some notation for the variables. I'm going to let B be the blondes, B complement is the non-blondes, M is the males, and M complement is the females. Now we can go back to the problem and start identifying the probabilities. 40% of the students are male, so that's just going to be the probability of male, or M, in our notation. The rest are female, that means 60% female. 20% are blondes, so that'll just be the probability of B in our notation, and the rest are not. The last piece of information is perhaps the trickiest and most important one. Out of the males, 1/8 are blonde. You should be able to recognize that this is a conditional statement. It's not a union, it's not an intersection. Out of the males is equivalent to saying, if I pick a male, 1/8 are blonde. So let's write down all the given information. We were told 40% are male, so the probability of M is 0.4, and therefore its complement, female, has to be 0.6. The probability of blonde was given to you as 20%, and therefore the probability of non-blonde is 80%, or 0.8. And that last piece of information, out of the males, or given male, the probability of blonde is 1/8, or 0.125. Again, that's a conditional probability. Don't forget, the given information goes to the right-hand side of the line. So out of the males is given male. And guess what? When we have a conditional probability like that, we also have a complement to it. If out of the males, 1/8 are blonde, then we also know that out of the males, 7/8 are non-blonde. B complement given M would have to be 7/8 or 0.875. So there's all of our known probabilities. Now we're ready to tackle the problem. Let's go back to the problem and see what they asked us to find. Part A, what's the probability that a student is both male and blonde? You should recognize this and this both is an intersection. So on part A of the problem, we're going to solve for an intersection. Male intersect blonde. Remember that intersections can be written in two ways. M intersect B can be the probability of M times the probability of B given M, or we can do it as the probability of B times the probability of M given B. One of those will do us good, and one of them usually won't do us any good. You have to look back at your given information. We know M and we know B given M. Therefore, we can use the first one here. M is 0.4. B given M was 0.125. Multiply them together and you get the intersection to be 0.05. Let's go back and do the second part of the problem. What's the probability that a student is either blonde or male or both? You should recognize either this or both as the union of two events. So on part B, we want the union, M union B. Go to your formulas. That has to be the probability of M plus the probability of B minus the intersection of M and B. The first two were given to you in the problem. M is 0.4, B is 0.2, and we just calculated the intersection in the first part. So M intersect B is 0.05. Put it all together and you will get 0.55 as the union M union B. And finally, let's look at the last part of the problem, our sex and hair color independent events in this problem. Show proof with the rules of probability. Remember that if two things are independent, a conditional probability has to be equal to the unconditional probability. So for example, B given M would have to be exactly the same as B. But we have both of these probabilities. B given M was given to us as 0.125. B was given to us as 0.2. Those are not equal. Therefore, these events are dependent. Okay, so in this case, we were able to solve for all of these basically just applying the rules or the formulas. There are times, though, when that doesn't always work. And another thing we can do here in a problem like this, a 2x2 problem, or 2x3 or larger, is we could set the problem up in a table. These are sometimes called joint probability tables, or I like to call them intersection tables. We'll put one of our variables on one side, so here we have blondes and non-blondes, and the other variable across the top, the males and the females. The problem told us that 20% of the people were blonde, so we're going to put that 20% out here on the end of the table. We'll call that total probability, or it's also going to be called a marginal probability. Non-blondes were 80%, or 0.8. The males go in this column. We were given 40% were males. We'll put that 0.4 down here. And the other 60% are females, which we'll put down here. The four other boxes, the four inside boxes here, are intersections. That is the intersection of this row and this column. So for example, this 0.05 here is the intersection of male and blonde. We calculated that 0.05 in the first part of the problem. Once we know that intersection, and we know these row and column totals, we now have all the other intersections too, because these rows have to add up to the totals, and these columns have to add up to the totals. So once we had 0.05 here and 0.2 out there, we know that this intersection had to be 0.15, and so forth. So by using the table, we might be able to see some probabilities that we could have had a hard time figuring out otherwise. So I usually encourage students to use things like tables to help them see things in the probabilities. A little bit more about these joint probability tables. You can actually develop them from frequencies, very similar to cross-tabulation tables that you had in an earlier module. We can start with frequencies of events and convert them to probabilities. As an example, suppose we have 500 students. 300 of them are male, 200 are female. Also, out of the 500 students, 350 are first-year students and 150 are second-year students. Finally, out of the 500, 250 are both males and first-year students. Again, let's set up some notation. I'm going to let M be the males, M complement the females, F is the first-year students, F complement is the second-year students. Set up a little table here. F and F complement, M and M complement. Now these are not probabilities yet because remember probabilities have to be numbers between 0 and 1, but we're going to show you easily that we'll be able to convert these to probabilities pretty quickly. Just filling in all the numbers. We were told that males, there were 300 males, so we put that in the total of column of males, and we have 200 females. We had 350 first-year students, 150 second-year students. Finally, you were given that 250 of the students were both male and first year. So that'll go in the intersection of that column and row. Again, once we have that, we can fill in all the other numbers because they all have to add up to these row and column totals that we had. Now, as I said, those numbers are not by themselves probabilities, but we could easily convert them to probabilities by simply dividing by 500 throughout the entire table. And if you do that, the table looks like this now. The probability of male is this 0.6 down here. We could have also seen that on the previous table. The probability of male is 300 out of 500. The probability of female is 200 out of 500, and so forth. So by dividing through by 500 in this table, we can convert these to probabilities. Again, the inner boxes on the table will be intersections. These four probabilities right here are intersections, and the outer boxes are what we sometimes call marginal probabilities, which we'll actually talk more about later. Let's do one more practice problem, because usually students need a lot of practice with probability. We're going to do a similar problem to our last one, but a little bit different. Suppose we have a breed of insect in which 40% have green eyes and the rest have brown eyes. 70% of the insects have long antennae and the rest short antennae. 30% of the insects have both green eyes and long antennae. And then once again, I ask you a series of questions. Again, identify the variables first. One obviously has to be eye color. We have green eyes and brown eyes. The other is length of antenna. We have long antenna and short. So again, we have a 2 by 2 problem. We have two variables, and each variable has two outcomes. Let's set up some notation. Let's let G stand for green eyes, and G complement is brown eyes. L is long antenna, and its complement is short antenna. Now we can write down all the given information. 40% had green eyes and the rest brown, so that's just the probability of G and G complement. Right here. 70% have long antenna and the rest short. So that's our next given piece of information. Probability of L is 0.7 and its complement 0.3. Lastly, 30% of the insects have both green eyes and long antenna. Again, this and this both is the intersection. So the last piece of information is the probability of green eyes intersect long antenna is 0.3. It's a little different than the previous problem. On the previous problem, I gave you the marginal probabilities and one conditional. This time I'm giving you the marginals and an intersection. Again, notice I could set all of this up in a table. The probability of green eyes is out here, 0.4, and brown eyes is 0.6. Long antenna is this column row total of 0.7. Short antenna is 0.3. And lastly, I gave you this intersection. Green eyes and long antenna is 0.3. That allows me to fill in all the other numbers in the table in case I need them. I might not. Now let's take a look at what the problem asked us. Let's go back to all of the things we were asked for. Part A, if one of these insects has green eyes, what's the probability that it has long antenna? If this, the chance of something else, is a conditional probability. So this is if they have green eyes, what's the probability of L, long antenna? So in part A, we want L given G. Go to your formulas and just apply the formula. A conditional L given G has to be L intersect G divided by the given event, in this case, the probability of G. If you look back at your given information and your table, we have all of this. L intersect G was 0.3, G was 0.4, so the ratio there gives you 0.75. Let's look at the second part of the problem. Find the probability that one of these insects either has brown eyes or a short antenna or both. Either this or both, as you'll recall, again, is the union of two events. So in part B, we want brown eyes, which is G complement, union with short antenna, which is L complement. Again, just go to the formula and apply the formula. A union has to be the probability of the first event plus the second minus the intersection. G complement was given to us as 0.6. L complement was given to us as 0.3. Now the intersection here, G complement intersect L complement, we can get rather easily once we've drawn a table. G complement intersect L complement is going to be this 0.2 right here. So we subtract 0.2, and this union is equal to 0.7. You might notice, using a table, you can kind of visualize a union, because a union is going to be everything in one of the rows plus everything in a column, but then don't double count the intersecting point. That is, we wanted everything in the G complement row, with this 60%, 0.6, everything in the L complement column, this 30%, but when we count this row and we count this column, this 20% or 0.2 got double counted. So we had to subtract it out once. So G complement union L complement is basically this plus this plus this. 0.4 plus 0.2 plus 0.1, which equals the 0.7 that we have right here. Part C again, I asked you an independence question. Let's go back. Is eye color independent of antenna length? Show proof. Again, one of the easiest ways to do this, up here we calculated a conditional probability. L given G is 0.75. But if two things are independent, the conditional has to equal the unconditional. L given G would have to be the same as L. And they're not quite equal. 0.75 is not equal to 0.7. Therefore, they are not independent, or we say they are dependent. Lastly, the last thing we want to look at here are the events brown eyes and short antenna mutually exclusive events. Well, you need to remember what mutually exclusive means. Mutually exclusive means they don't intersect. Brown eyes and short antenna. Now, it's real easy to find the answer to this question if you've drawn a table. Brown eyes is G complement. Short antenna is L complement. The intersection of those two is right there, where the row and column intersect. That intersection is 0.2, which is not equal to 0. So as long as this number right here is not equal to 0, they are not mutually exclusive. So since the intersection is 0.2, which is not 0, no, they are not mutually exclusive. You will find usually in a lot of books and assignments, you will find a number of problems that sometimes give you joint frequency tables like this and ask you probability questions from them. And again, you can either use the frequencies to answer the question, or you can convert the whole table over to probabilities as we did earlier. Okay, and that's the end of part 3. We have one more part to the chapter material. We actually have 2 more formulas to finish up, but actually they're just extensions of things you've already seen. Everything else in probability is really an extension of unions, intersections, independence, and so forth. And we'll get to that in part 4.